All right, so we left off here talking about this addition of HX to a conjugated diene. It follows the same pathway, same mechanism as addition to a alkene, but with a conjugated diene, there's a common intermediate. And I said that we get two products, but there's a common intermediate to get to each one of those products, and it's this allylic carbocation that I showed here. All right. So we're gonna work through this example down here, and keep in mind whenever you do addition to a conjugated diene, anytime you do addition to to a conjugated diene, both alkenes are equally susceptible to reaction. So you have to think about this in terms of which alkene is reacting. So we're going to take this first problem right here. It says use the product from the reaction, which we did the other day, and propose a mechanism for the product formation. All right, so if this is my alkene, we're going to start out with the red alkene. This is my diene, sorry. We're going to start with the red alkene. All right, and it gives us down here, it gives us temperatures. So let me take this and I'm just going to put it below. And then we'll go through the mechanism. Right, so up here, let's just go through the products. And then, so here, if this is the alkene that we're working with, right, we can assume that the intermediate would look like this. So that doesn't change. And this is a positive charge. This is an allylic carbocation. All right, so we can assume if we use that red alkene that these are my two products. One of them from direct addition or 1,2 addition. And then one from what we call 1,4 addition. And I'll explain that. I'll explain that when we go through the mechanism. Let me fix that. So these are the two products that you'll get from that intermediate. So now let's talk about how you would get that. All right, because one of these products, this one, which we call a 1,2 product, is the low temperature product. And then this one, 1,4 product, is the higher temperature product, right? Because remember what one of the things I said about this reaction is that it is temperature controlled, right? So at lower temperatures, you get one product predominating, and then at higher temperatures, you get another product predominating. All right, so let's go through the mechanism. And then we can discuss why we see what we see. Right, so in the so we're using this alkene right here, and we're going to react that with HBr. Right, this happens just like it would, just like you remember it from organic one. right? You're going to do a proton transfer where the alkene is your nucleophile, and you lose bromine here, and then you end up at this intermediate. Right? It's always an allylic carbocation. It's never, I wouldn't put the plus charge here, even though I could, right? But for this particular reaction, uh, addition of HX to a conjugated diene, your intermediate is always the allylic carbocation, right? Always. Right? So now over here, let me do this. Let me number this. Right? This is, if I'm using this alkene, I'm numbering here 1, 2, 3, and 4. Right? And that's how I get that product designation, because over here, those numbers are still the same. 1, 2, 3, and 4. So if I attack the carbon that's numbered 2, that's going to give me my 1, 2 product. If I attack the carbon that's numbered with number 4, that's going to give me my 1, 4 product, right? So here the bromine can come in. It's negative. It can attack directly right there at that carbocation, right? And that'll give me this product. Right? And again, if I number it, this is 1, that's 2, that's 3, and that's 4. All right. Questions about that? And then the 1,4 product, you can also think about like a resonance product. That's another way to think about it. It may simplify it if you think about it like a resonance product. So if I take this pi bond and shift it over, we can say that the 1,4 product is the resonance product. Right? Because if I do resonance on that cation, then this is what I get, right? The double bond is now here and the plus charge is here. And then it's from here that bromine can attack. Right at that carbon. So then my product from the 1,4 addition would look like this. Right, and again, same numbers, because I'm on the same, using the same intermediate. So this is 1, that's 2, that's 3, and that's 4. All right, questions about that? So the 1, 2, and 1,4 products, you're going to get both, but depending on the temperature, you're going to see more of one than the other. So there's going to be a ratio of products depending on the temperature. So at low temperature, this is the product that's going to predominate. And then at higher temperatures, that's the product that's going to predominate. So up here, when it asks us, well, no, it's actually down here. Actually, let me do this. So here, when it asks us about this, the major and the minor products, at 0 degrees, right? At 0 degrees, which is low temperature, the major product is going to be this one. All right, so this is low temperature, this is major, right? The 1,2 product. And then, of course, at 0 degrees, the minor product is going to be this one. So the 1,4 product is minor at low temperature and is major at high temperature. So that's the difference is that the reaction at low temperature is under what we call kinetic control. Right, and then at higher temperatures, it's under what's called thermodynamic control. If you watch the video that I sent out, then this is not, you may not fully understand it, but it shouldn't be foreign to you. Thermodynamic control at higher temperatures, right? Questions about that? All right, so let me explain a little about kinetic control and thermodynamic control, and then we're going to take that blue alkene, we're going to do the same thing with that. All right, so let's talk about kinetic versus thermodynamic control. So can somebody tell me, if you watch the video, tell me what the difference is?
With kinetic control at lower temperatures, the product that forms the fastest is going to predominate, but in thermal control, the product that's more stable is going to be formed first, I think.
Good, you're exactly right. Thank you for that. 1 second, let me get my handwriting together. All right, so kinetic, this is all based on either activation energy for kinetic control or delta H for thermodynamic control, right? Because it's the enthalpy delta H that controls equilibrium, and it's the activation energy that controls reaction rate. So if a reaction is at low temperature, we say it's under kinetic control. What that means is exactly, was that you, Cecilia?
No, that was Asia.
Okay, good. All right. So yeah, so thank you. Under kinetic control, right, we're concerned with the rate of product formation. And this is controlled by the activation energy, or delta G double dagger, right? That's what we're concerned about, the rate of product formation. All right. And then under thermodynamic control, what we're concerned about is product stability. So product stability, right? This is delta H, right? The enthalpy. So if a reaction is under kinetic control, what's going to govern that reaction and govern the product distribution is which product is forming fastest. If it's under thermodynamic control, it's understood that there's enough energy present that the more stable product, or there'll be enough energy to get to the more stable product, which I'll talk about in a second. I'm gonna pause right here because we do have our guest from Amazon. So let me, all right, where was I talking about? Kinetic control, thermodynamic control, yeah. All right, so let me talk about this from an energy perspective. So like if you watch the video, then this is this is not foreign to you. But if you have an energy diagram and on the y-axis, x-axis is time, y-axis is energy. If we're under kinetic control, so we're under low temperature conditions, right? And you're at your, change pens, right? And you're at your intermediate, which is here. And that intermediate can go to, so this is one product, and then this is the other product. Let me change the, right? If you look over here, so we'll say product 2, and then this one will be product 1, right? What you'll notice is here, there's a difference in activation energy. So the activation energy for product 1 is here, and activation energy for product 2, and that's the energy to go from here to the transition state, is here, right? So if you're at low temperature and you have an opportunity to form, and you go, keep in mind we're starting at the intermediate for this reaction, right? And you have opportunity to go to either product 1 or product 2 at low temperature. There's not enough energy around to get over this hump, right? That activation energy is too high, right? So under low temperature, under using low temperature conditions, the product that has the lowest activation energy is going to predominate, even if it's not the most stable. Because if you look over here, the difference in energy between product 1 and product 2 is actually higher in energy. I'm sorry, product 1 is higher in energy than product 2. Right, if energy is increasing in this direction. But because you're at low temperature, product 1 is the most accessible of the 2 because it has a lower activation energy. So the rate is increased. I'm not gonna say no energy. I'll say insufficient energy to get to product 2. Right, so the rate for product 1 is faster. There's not enough energy to access product 2, so product 1 is going to predominate, even if it's less stable. That's what we mean by kinetic control. Right, if you go to higher temperature, right, and this again, this is increasing energy. This is time. Right, and you add your intermediate here. The difference at higher temperature is that you can actually, at a higher temperature, you can set up an equilibrium. This is what the difference is. So you can set up equilibrium. Get my spelling right. All right, so here you'll have so this will be P1, this will be P2. Right, so you notice P2 is lower in energy than P1, still has a higher activation energy. So this is still delta G. And over here, same thing, right? But at higher temperatures now, you have more energy available, right? So you can get over the activation barrier to get to P2. So here you set up an equilibrium. And what happens is, since P1 is less stable, right? P1 can actually get converted back into the intermediate and then get converted into P2. I'm gonna abbreviate intermediate. Right? So that's the difference. At higher temperatures, even if you have a less stable product, everything is reversible. Right? So you can go from P1 back to the intermediate, which is here in the middle. And then you can go from the intermediate to the more stable P2 product. So at higher temperatures, you got more energy. The activation barrier is no longer an issue. So P2 is going to predominate at under higher temperatures if it's the more stable product. So that's what that means. Because up top, remember we said that the reason P2 wasn't accessed as readily is because at low temperature, there's less energy. So it's harder to get over that activation barrier. But when you increase the temperature, you add more energy to the system, right? And so that means that the activation barrier is less of an issue. And with that, the more stable product is always going to predominate, because we talked about this early, way back when we first started this class. Everything in chemistry happens for one reason, and that's to go from a less stable state to a more stable state, right? And so that's why certain reactions happen. That's why certain reactions you need to kind of juice up and add some energy, because in order to get them to go, you have to get over that activation barrier. And maybe the products, or maybe it's an endothermic reaction, but once you get to the products, you can't go back. But in this particular case, if the temperature is increased, so is the energy. And if the energy is increased, then you're able to access P2, which has a higher activation energy. So with that equilibrium being set up, this is thermodynamic control. Right, and that's the difference between those two processes. One is based on reaction rate, the other one is based on stability, well, product stability. All right, any questions about that? So let's apply this information to this example right here. Right, so we're saying if both products, we're gonna look at the kinetic products, because if the other alkene reacted, the blue one, then this would be the kinetic product. All right. So both of those are kinetic. And the question asks, if it says if we take both of those low temperature products and warm them up to 40, right, we could change the product distribution. We could increase the amount of the 1,4 product. So the question is, how do we do that? Right. So if this is the intermediate, and again, that's talking about going from the less stable product back to the intermediate, and then going from the intermediate to the more stable product. So this is my intermediate. How do I get there from here? We've seen this before. What happened going from the product back to the intermediate? What changed?
I'm sorry, Dr. Russell, I think I missed your question.
What changed going from the kinetic product on the left back to the intermediate? What's the difference?
The bromine left.
Okay, so bromine acted as a leaving group. Have we seen that before? Under what reactions have we seen that?
Is it the alkyl halide? Was it the alkyl halide reactions?
One of them, yeah. But which one?
Oh God, is it what is it? Is it PDR?
Mm-mm, 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 mm-mm. Think about something that we just did. Then we just studied substitution and elimination.
Yeah.
And don't we have a pathway, a substitution pathway and an elimination pathway that starts with the loss of a leaving group? Which one was that? Was it SN2 or SN1?
SN2.
With the leaving group leaving first?
Oh, I guess it was SN1.
Yeah, it's SN1. So it's a SN1 type mechanism. So I could show that. Can I show that going from here to here by just showing the bromine leaving?
Yeah.
So that'll get me back to the intermediate. Now, how do I get from the intermediate to the other product? How would you show that? Because the point is, if I have a product that was formed under kinetic conditions, I can warm it up and then get it to decompose back to the intermediate and then react again to become the thermodynamic product. That's the point I'm trying to make. So how would I show the intermediate going to that other product?
Well, you're making it, when it's thermodynamic, it has to be more stable.
Mm-hmm. But look at the product itself.
So it has to go into resonance.
Okay.
The ring.
You're saying do that,
Yeah.
and that's going to get me to. I'm trying not to jumble this stuff up. That's going to get me to here. To here, is that right?
Yeah.
And then how do I get from there to here? You're right. Don't I just need to react the bromine with it now, right?
Yeah. Yeah. That's what I was saying that, but I was on mute.
Okay, that's all right. All right, so that's the gist of this kinetic versus thermodynamic discussion, is that you could sometimes, if you're working under kinetic conditions and you want to change the product distribution, you just need to change the temperature. All right, because then you can set up this equilibrium. You go from the low stability product back to the intermediate, and then if the temperature is higher, you can get to the other product. It was 9:52. All right, we got to stop here. We don't have class on Friday, obviously, because of the convocation. I'm still gonna post the exam. I'll post it like I always do, and then I'll leave it open until Sunday. And we will have a recitation tomorrow at 7. If I'm not up here all day tomorrow, then we'll do that. All right. Any questions?
No, not right now.
All right. And if before you log out, hold up. He just sent it to me. I'm gonna post this link in the chat for that competition. We send it in a direct message. But you can click on that link or copy it and paste it, save it, and hopefully you'll apply for that competition and win the money. All right. If there are no other questions, we're going to stop and we'll pick up on Monday.